So welcome to the photogrammetry course that I'll be teaching here over the next 2 semesters at the University of Bonn. My name is Cyrill Stachniss. I'm a professor for photogrammetry, and this is a bachelor's course going over 2 semesters, Photogrammetry I and Photogrammetry II, where we want to dive into the basics of photogrammetry, doing 3D reconstruction, doing semantic interpretation, doing image analysis tasks, and introduce you to the basic techniques and algorithms that are today used when we are working with images. So let's start without saying what actually is photogrammetry. So photogrammetry is the task of measuring with light or measuring with photographs or photos. And it comes from Greek origins. The words photos means light, gramma means to draw, and metron means to measure. And putting that together, photogrammetry and actually means we are using typically images, camera data, in order to perform measurements. Measurements about the environment. What does the environment look like, for example, is a typical 3D reconstruction task. Or interpreting what we are seeing, adding semantics into the game is also something which becomes more and more important over time. And we may even relax the question of light or photographs here a bit more and talk about electromagnetic waves. And then it's a bit more than just the visible spectrum, for example, that we may take into account over here. So after having clarified where the word photogrammetry actually stems from, so what is photogrammetry from a more formal definition point of view? So it's defined as the estimation of geometric and semantic properties of objects based on images or observations from similar sensors. Okay, so geometric properties, I think, is pretty clear. It's where's an object in the world, how does the 3D geometry look like, where are surfaces, what kind of shapes are around, how are the shapes oriented. These are all geometric properties about the environment or objects in my environment. Then there are semantic properties. So semantic refers to the interpretation of things. For example, saying, oh, what I'm seeing there is a building, or what I'm seeing there is a human. Those pixels actually stem from a human. So adding this kind of semantic label or this human-defined label to a measurement is something that we often refer to as semantic information. And we are often interested in estimating them as well. And we are doing this based on images or observations from similar sensors. So the question is, what are similar sensors? And this is the question of how narrow you want to focus this. So this could be just a photo camera, maybe a video camera is also pretty similar because it basically shoots photos at a high frame rate. We, however, want to relax that much more. We may say, okay, what about a sonar sensor, or what about a laser range scanner, or some other sensing, hyperspectral sensing? What about your smartphone? These are all valid questions, and I would actually include all this sensing technology into what we see as photogrammetry, although in this course here we are mainly focusing on cameras. So in this course we will restrict ourselves mainly to, let's say, monocular cameras or stereo cameras. Also we're looking at multi-view or multiple view reconstruction later on, but we are mainly focusing on cameras. But it's not a restriction for photogrammetry itself. So laser range scanners, for example, are great tools for doing 3D reconstructions or even for doing semantic estimation from them. And that's also something that I'm doing in my group, but it has just kind of a smaller part here in at least this bachelor course. So if we break it down a bit more, semantic and geometric properties from image data, then we may see this. So one is related to estimating geometry. So you can see the building over here, and those red points overlaying the buildings are actually 3D points that have been estimated from cameras, from a drone flying on a building and then overlaid with this 3D model, so we can estimate how good our 3D reconstructions. So this is basically the geometry part, and the semantics part could be, I have this image here. This is a field, a top-down view of a field here next to Bonn. This is our sugar beet plants, and these are weeds. And the semantic interpretation could look like that we say the yellow pixels over here would be labeled, as green over here, not yellow, is a sugar beet plant, and everything which is labeled here as red is a wheat plant. So this is a semantic interpretation based on that image data. And these are kind of 2 key problems that we experience in photogrammetry. And we can use this information for a lot of different tasks. We can passively collect the data like camera images with a drone, on a vehicle, on a mobile mapping system, with our smartphone carrying in our hand, taking pictures of the environment. Or we can take this information and feed it more into a closed loop system that the perception that we're actually generating treats how measurements are taken. And then we come very close to robotics tasks where we have a robot equipped with a camera, it perceives the environment and acts based on what it sees. And again, for this information, geometric information as well as semantic information is important, and then maybe other aspects come into the game. How quickly can I actually compute this information? Can I do this in an online fashion? These are all tasks which are relevant for applications that which are using concepts from photogrammetry. So what do we typically measure if we are talking here in photogrammetry or typical photogrammetric problems that we would experience in this course? For example, camera localization is one thing. How do we know where a camera is just based on images? So the camera which takes images, if we know something about the objects in the world, can we actually say where that camera was when it took the images? And it turns out, yes, we are actually able to do that. Given if we know where cameras, can we determine where objects are located in the scene? Yes, also that's something that's doable. It always depends a bit. Can we do this from a singular camera image? Do we maybe have more camera images? Do we need some additional information about the environment? These are all valid questions, but that's something we can do. We can also perform 3D reconstruction. If we have multiple images of an object, so we take our camera and take a lot of cameras of an object. Can we do a full 3D reconstruction of this? Yes, we can. We may miss some information, maybe some scale may be hard to obtain, but maybe I can add this as an additional information in there to in the end get a beautiful 3D reconstruction. Often when we look into image data, we are faced with the question, is something similar? Is image number 1 similar to image number 2? Or what I see in image number 1 is actually the same object that I'm seeing in image number 2? And this is kind of similarities in data association. Making these correspondences is a very challenging task because interpreting images is hard or can be very hard, and wrong data associations can actually screw up your state estimation systems quite substantially. So dealing with wrong data associations or developing techniques in order to fight the right data associations is something which is key in here. We may want to look also into object detection or semantic interpretation, semantic segmentation in an image, which means, for example, that for every pixel you want to assign a semantic class to this. These are all tasks that we do when we talk about making measurements. And these are also things that we are going to address, at least partially, in this Photogrammetry I and then later on Photogrammetry II course taught here at the University of Bonn. So what are disciplines which are related to photogrammetry? Where does photogrammetry come from? And I see it being intersecting with different disciplines, mainly 4 disciplines. So traditionally, photogrammetry is part of genetic sciences. It's what's called traditional photogrammetry, working with camera images, originally starting, for example, to build maps of the environment, aerial photography, for example. But it's also very similar to computer vision. A lot of the tasks that we do in computer vision are actually photogrammetry tasks. And today in photogrammetry, we're also using computers to solve those problems. So with the advancement of computers and digital cameras, which are now around since actually quite a long time, photogrammetry and computer vision actually have grown together quite a bit. And although the computer vision community is typically a much larger community, it often has a background more from the computer science side, and photogrammetry comes more from an engineering side. They both have substantial overlaps in those fields. Also, in photogrammetry as well as in computer vision, machine learning plays an important role, especially within the last, let's say, 10 years or even more. Machine learning became more and more important to solve key problems from photogrammetry and computer vision. So it's unthinkable today to do photogrammetry or computer vision free of learning algorithms. This only holds for a small subset of developments. A large number of developments are heavily impacted by machine learning. So if you study photogrammetry or computer vision, you will get in touch with machine learning algorithms. And also robotics is a great, let's say, application area for all those developments here, because typically robots are equipped with sensors. They sense the environment. They need to interpret what's going on. They need to build semantic models. They need to build geometric models in order to, for example, plan a path, navigate through the environment. If we take what's a robot a little bit broader, we can think about this as autonomous cars. We can think about this about autonomous aircrafts or UAVs which fly autonomously, copters which inspect the environment, which may do inspection tasks and then actually coming back to the original engineering disciplines quite substantially. Even satellites you may see as a mobile sensing system or even as a robot which does certain tasks externally controlled or supervised, but certain corrections also on their own in order to provide measurements and observe the environment. So these four disciplines are heavily connected with each other, and we will get in touch with all those areas here in the photogrammetry course. So we will touch computer vision, obviously. We will have an introduction to machine learning, and especially for the semantic interpretation, machine learning is important, and robotics and typical mapping or simultaneous localization and mapping tasks that are relevant in robotics will also pop up here at the one or the other part of that course. And so those topics will be touched here in the photogrammetry lectures. If you kind of now connect this a little bit more with the disciplines, so photogrammetry itself has been developed for surveying purposes and thus is part of the traditional geodetic sciences. So every geodesy faculty typically has computer vision or covers computer vision in some form. We can also see it as an optical form of remote sensing, actually remote sensing stemming out of photogrammetry, but now being actually a fairly large field if you compare it to the original photogrammetry field. So remote sensing became maybe even more popular than core photogrammetry itself. It is, again, as I said, strongly connected to computer vision and image processing for the task of generating measurements. So in computer vision, maybe in some parts a little bit broader, photogrammetry often focuses on actually getting measurements and then do something with those models that we actually have been building or using them for analysis. And there are very strong links also to robotics, especially in the state estimation area. So performing state estimation in photogrammetry and robotics is actually extremely similar, maybe using a slightly different notation, but a lot of the tasks that are done in both fields have a very high overlap and can benefit from each other. And again, in all those areas, machine learning plays an important role, especially with the advances of deep learning over the last decade that's changed those fields quite substantially. And doing photogrammetry, computer vision, robotics completely free of learning is not something which happens very often. In a lot of components, some aspects of machine learning will actually play a role. But let's go a little back now to kind of traditional photogrammetry using camera images. So what are the advantages of cameras? And one of the things, it's contact-free sensing. And you may ask yourself, why should I care? Why is it important that it's contact-free sensing? This has several purposes why contact-free sensing can be a good thing. So you may deal with, let's say, toxic materials, things you shouldn't touch. It may be very hot or very cold. You may destroy the material because it's very sensitive, or it's even inaccessible to you, that you can't reach it, but you may be able to see it. And so there are a lot of reasons why contact-free sensing is great, although cameras also clearly have their disadvantages, but in general, contact-free sensing is something which is great. So a lot of things become easier if I don't need to touch the object, and being able to approach all those materials is something which is relevant and which is great. There are other reasons or other advantages of photogrammetry. It's relatively easy to acquire a quite substantial number of measurements. So if you think about your image, every pixel in your image tells you something, measures light coming from a certain direction. So with images, you can actually get a large number of measurements, and collecting multiple images is very easy. Even if you think about a video camera, which generates a constant stream of images, observing an object, that's something which is fairly easy to do. And with images, you're also able to cover comparably large areas. And it's not kind of has a fixed scale. So you can go closer to objects, and then you get high resolution images. You can do a very precise reconstruction, or you're further away, you have a lower resolution of, in the end, whatever pixel with respect to centimeters or meters or millimeters in your scene. whatever, ground sampling distance, for example, if you work with UAVs. And therefore, you're very flexible in the measurements that you're actually generating, which is really great. It performs 2D sensing, but with multiple 2D sensings, we can actually generate 3D sensing. They have 3D cameras, which add some external light, for example, into the scene, and this kind of recover the third dimension, or you use 2 cameras in a stereo setup, which also, if you know the data station, at least tell you something about the 3D geometry of the scene. So they are actually great advantages of using those cameras. Other advantages is that you can actually record dynamic scenes. So just using a video camera, for example, you can actually track the motion of objects. You can then do predictions about what's going to happen in the future. And also we as humans can interpret the data really well, because we can look at images and say, okay, this is an image, this means this, oh, what happens there in this image. I can, as a human, can interpret the data later on, which is much easier compared to a laser scan that I take about the environment, or just doing point measurements of certain distinct points in the environment. If there's a mistake in there, it's very hard to recover from those mistakes. It's much easier to do this if you have access to the original images. Also compared to whatever just simple point measurements, we can do much more in terms of estimating also the semantics. That works especially well because, as I said, we as humans can interpret the data. We can label or annotate that data quite easily, and then this supports machine learning algorithms in order to add additional information or estimate semantic informations in there. And so the data itself, the images that I measure are the core measurements on which all the interpretations are done. So it's also a good documentation of the measurement process that I actually have my original images always in hand. And it allows for fairly automatic data processing. So especially with the advancement of computers and parallelized GPUs, for example, I can process the data automatically and also in a very efficient and very fast manner, which then allows me to do, for example, real-time processing. So there are a lot of great properties of cameras and why cameras are great sensors to use, and that's the reason why we actually stick with it. However, there's no free lunch. There's always a downside. If something is good on one thing, it probably has disadvantages on the other side, and the same holds for cameras. So the main question is, what are the disadvantages of using cameras? And if you step back a bit and think about it, becomes pretty obvious. One of the things, for example, you need light. It's so easy that most people probably don't think about it, but if you think that 50% of the time it's actually dark outside, if you don't add an own light source, you can only do measurements 50% of the time, which is actually not too much if you think about it, of an automatic process. Of course, you can add lights, you may have cameras which are super sensitive or things like this. Yes, you can fix things, but with a laser scanner, for example, you can perfectly works in the dark, same way it works during daylight. And there are certain disadvantages of cameras, and being required to have a light source is probably a very, very big one. What cameras also do is they in the end measure only intensities that come from certain directions, so light intensity. How much light is reflected from a certain direction? That's what your camera actually provides to you. And this is, for example, not a range information. You don't know how far objects are away. From a single image, you only know where a point is located on an array in a direction vector, but you don't know how far the object is actually away, which is clearly a downside. Also, you have visibility constraints or occlusions. If objects occlude themselves, you can't look through an object, at least through most of the objects, unless the transparent ones, which are also a challenge to deal with, by the way. You have constraints that it's hard to look through something, and this is clearly a downside of cameras, which other sensors, maybe radar, can do a better job with. And as I said before, this missing depth information is actually a key thing, also something that you will start to struggle with, at least in the Photogrammetry II course, on how can we recover 3D information just based on those 2D measurements. And again, there's no free lunch. There's always a price we have to pay. Either we need to have multiple images and have a good data association, or we need to add some prior information to the scene. So the information loss by going from the 3D world to a 2D image plane can cause serious headaches and make certain computations fairly complex. And that's one of the challenges that we have in photogrammetry. And also what may be relevant, there are some other measurement techniques which may be more precise. Again, we are very flexible in terms of how close we can go to objects or how broad we get an overview with the camera. That's great, but there are other sensing technologies for specific applications which are more precise and provide a higher overall accuracy in the end. And that's something, if accuracy matters, cameras are not always the best thing. It's important to note that cameras basically are direction measurement devices in terms of light intensity coming from a certain direction. We often reduce this light intensity measurement to saying a point measurement in a certain direction. So for example, the two peaks of those mountains over here. So the light from those two peaks of the mountains is our reflected path through my projection center onto my camera image. So this should be illustrates the 3D world. This illustrates my camera image. And of course, this point, mountain peak, is not explicitly a point. I basically just receive the intensity values and I say that's a peak, or my automatic algorithm says that's a peak. And then I know that this is a 3D point mapped onto the 2D environment. But basically, points in the 3D world are just mapped onto a point in an image, so from a 3D information to a 2D information. And if I only have the image, the only thing I know that this point must lie on that straight line through the 3D world, I don't know how far it is away, because I'm basically having a loss of information going from 3D to 2D. I'm throwing away information, and I can't recover this information easily. So based on the image, I only know in which direction the peak of the mountain is. I actually don't know how far that peak is away. And that's this loss of information, the loss of the third dimension that I'm actually struggling with. In Photogrammetry II, we will look into 3D perception, taking multiple images into account. Because what I can do is, if I have multiple images and I know, for example, where those images have been taken, and I can identify points which I see in image number 1 and image number 2, so whatever, this is the second point, this is the first point, and I know those correspondences, I can use this information in order to perform, in this case, a triangulation in the 3D world, and then say, okay, this part of the building, the entrance must be here, and the right part of the entrance must be here in the 3D world. So if I have information about the environment, I can actually generate 3D information based on 2D images, but then I'm required to have multiple images. But that's something that we're going to cover in the second part of the course in the Photogrammetry II part. So we can think about the process of going from the object to the image. So what impacts the image generation process? So what we have is, we have an object in the 3D world which has certain properties like geometry, location, type, and we have our camera, for which we know what are the internal parameters of our camera, like what lens are we using, what are the properties or internal properties of my camera. These are called intrinsics, and what are the extrinsics, so where is my camera located, basically the location orientation of my camera. If I have the objects in my scene and my camera, I can take a picture of the camera, and physics does that job for me. So I press the trigger button of my camera and it will generate an image, and the output is an image. That's great. So that's how we generate an image. From the world to the image. That's how we actually generate this approach. What we are, however, faced with in photogrammetry typically, we have this image and we want to revert this process and know something about the objects or about the camera. And there we don't have this magic block physics in here, which does all the job for us and generates this image. So we need to basically invert physics, so to say. So in this inverted mapping, we have images taken from our cameras, and we have some hopefully smart algorithms which allow us to solve certain tasks. And then we add knowledge, or we add some physics properties, and there are some rules and some other background knowledge, maybe that's specific to the scene, and we need to give that to these algorithms. And then we can infer something about the objects and about the camera, and maybe estimate the intrinsics, extrinsics, or the geometry of the object, location, or what type of object it is. And we are typically faced with this inverted mapping. So we have our images. We need to develop algorithms that tell us then something about the camera and the object. So the core is actually this part over here. Developing new algorithms, or algorithms in general, hopefully new algorithms and interesting algorithms, which can exploit the measurement that we have, so the images, exploit something physics or common rules that we have that hold, and maybe some background knowledge about the scene, and put that together in order to come up with the best possible explanation of object properties or camera properties. And that's typically the task that we are doing. And the outcome here can be geometry, can be type, so semantics, and same holds for the camera. So basically going from the image to the interpretation, or from the raw data to the estimated geometry, these are tasks that we are facing with, and these are the key problems in photogrammetry that we are typically addressing over here. So the next thing we can actually look into what is actually the challenging task if we think about the interpretation of those photogrammetric problems. And there we can look into the human perception. So how does the human perception system works? So we have some object in the world, which light shines on the object. The eye basically sees the light or perceives the light, gives the information to our brain, and then we generate an interpretation. So we have this first part over here, which our eye does, our brain does, leading to an interpretation. And the key question is, what's the more challenging work? Who does more work, the eye or the brain? And so that's a valid question to say, what is it that actually does most of the work? Is it kind of the sensor, or is it the interpretation of the sensor signal? And in order to get closer to answering this question, we can actually do an experiment. And so this experiment which has been conducted, there was a person which was blind from birth on, so has never actually seen the world, and a camera that records the scene. And then an image was kind of printed onto the person's skin, basically using a dot or generic a dot for each pixel. So not really printed, but like similar to a braille device, where you turn the image, just the black and white image, into onto the skin. The question is, can that person actually see? And it turns out, yes, this person can see, in the sense that this person can recognize different objects and interpret the scene just by mapping the camera signal onto the skin. And so from this we can actually conclude that the brain is probably doing the majority of the work and the hard part of interpreting. And it's not necessarily the eye that can do this, because even with our much simpler senses, like the sense of touch on our skin, we are able to interpret the scene and interpret what's going on. So the brain seems to do most of the work, and as a result of this, one of the motivations why algorithms are so central. And this was also, if you think about this inverted mapping that I've shown a few minutes ago, there you see the algorithms are at the core, and these are the building blocks, the tools that we are developing, the core of our research, that we then can use as tools in order to simplify this process. And most of the brain power actually goes in there. So estimating the geometry of the scene and interpreting semantics from images requires brain power. And the sensor, of course, the better your sensor, typically the better your interpretation will get, but brain power is important. And the central element of brain power, or at least simulating smart behavior, are algorithms which solve certain problems. This can be learning algorithms, and that's one of the reasons why learning algorithms are so popular in our discipline, but don't have to be learning algorithms. There are also other well-designed algorithms which don't have machine learning involvements in here, which produce a great output and solve tasks partially in an optimal manner. But these algorithms itself are key for understanding what's going on, for understanding the problem, for implementing a solution which solves the problem, and therefore programming is a key tool, because programming is the toolbox that allows us to actually implement algorithms, to realize algorithms, to test algorithms on real-world data. And that's also one of the reasons why in this course programming plays a role, especially in the homework assignments. You will have tasks of implementing algorithms that I'm presenting here to make sure you understand them and you can actually put them in place and interpret, work on image data, change images, for example, or interpret image data, or doing some reconstruction tasks or localization tasks based on that image data. And that's kind of key in here. Then I would like to look a little bit into typical sensors. So what are sensors that I'm talking about here? So they, on the one hand side, are so-called industrial cameras that you're using, which are typically connected to a computer, some frame grabber card, getting the data and getting automatically processed. This is a common setup to use this on industrial systems, but you also have other sensors like consumer cameras do a really good job today in acquiring high-resolution images, and especially the digital cameras that you can actually buy today are awesome sensors that you can use for 3D reconstructions. And even the quality of your phone increases year by year and can do really good 3D reconstruction tasks today. Also pairing the camera data with other sensors inside your phone, like an IMU or gyro or GPS sensors or LiDARs even. So by combining those sensors together, you can actually really do a lot. Another sensor that most people probably haven't seen or haven't seen very often are cameras used in airplanes, aerial cameras. This is then more towards the direction of remote sensing. So this is the Microsoft UltraCam, which was used in Bing Maps and basically generating this aerial high-resolution imagery, also using different spectral bands in order to generate high-resolution image material, observing the surface or the urban environments in a top-down nadir view or close to nadir view, and provide relative information. Collecting this, you can do the same thing basically on satellites where your resolution decreases, but the area you cover is much larger. These are also key sensors that are used for monitoring the Earth and doing interpretation using those algorithms. And other typical sensors, a little bit less common, let's say it that way, but still commonly used, are laser rangefinders. These are active sensors which emit a signal and then measure the time it takes until the laser beam hits an object, is reflected to the object, and measured again in the sensor. And with this time of flight principle, you can actually measure the distance to the object, partially combined with cameras, and so that you actually get 3D information out, which is a very useful tool. They're typically also very accurate in their depth measurements and can outperform cameras, especially with respect to the depth measurements, but also cameras have their advantages. So it's actually great to combine laser scanners and cameras together to kind of get the best out of two worlds. What I now want to do is I want to dive a little bit into some application and give you some examples why the tasks that we are doing are actually useful. So what can we do with the techniques that we are going to develop here in this course so that you will learn and hopefully understand in that course. First application is generation of maps. How are those maps actually being generated? And one way for generating those is based on aerial imagery. And this is an aerial image taken, overlaid here with the map. So we can use this aerial data to enrich our maps, even to use it to generate the maps. We will also look into the creation of so-called orthophotos in this course, that is basically performing a correction on those aerial images, that you can actually directly perform measurements in those images, which is very useful for exactly those tasks and aligning those aerial images with existing map information, for example, or other 3D information. And so this is a core part, acquiring information about the environment to support the map building process. We also may go further and basically perform or generate full terrain models of the environment. This can happen from satellite data. This can happen from airplanes, or may happen from small-scale drones. So this is an example of a small-scale drone, whatever that size, flying over the environment with the cameras equipped, perceiving in this case an agricultural farm. So this is here in Kleinaltendorf next to Bonn, in our experimental farm in Bonn, and then interpreting the camera data that they're seeing. And this is one example of how you can actually use this information in order to support precision farming applications or breeding applications. By observing the field, you can run these algorithms to interpret the scene, so the semantic interpretation as well as geometric reconstruction, in order to estimate, for example, where is there a high wheat pressure. So these green dots are the sugar beet plants, and those purple dots over here are wheat plants, and you can analyze the field and then perform, for example, some form of wheat control. You can also go a step further and use the same technology to, for example, support breeding applications. So what happens in plant breeding, for example, you have those test plots where different varieties of a plant are actually planted, and the goal of the breeders is to monitor the task and see which plants performs better under certain characteristics. And for that, you can actually fly with a drone over those fields and analyze the image data, and then actually break down and estimate the instances. You can count every plant, you can look how large that plant is, what's the perimeter of that plant, what are boundaries, and can derive other phenotypical parameters from just the camera images that we have when we're flying with those small-scale drones over the field. And that's a great tool for using this photogrammetric techniques, to provide additional information to other disciplines and enable them to exploit this information and solve relevant tasks in their domain. I have another example here. This was a project of a research unit that we have been executing here at the University of Bonn for quite a while. This was the project Mapping on Demand, where the goal was to develop UAVs, which can perform navigation and monitoring tasks, combining GPS information and camera data, for example. So this is a UAV flying around, being tracked with a GPS IMU-based system where you can estimate where those drone is when it's flying over the ground. And then we have cameras on board, and we can estimate based on the camera a visual odometry. So these are two stereo cameras looking forward, two stereo cameras looking to the back, and a high resolution color camera, so that you can then extract features, so distinct points in the scenes, and can make data association between those points. So this point in image number 1 is this point in image number 2. And through this data association, I can actually perform 3D reconstructions. And also can use the camera to estimate where the system is in the environment. And can combine this with, for example, IMU and GPS information, so that I can actually provide a consistent track of georeferenced images of the environment. And you can actually show that this works fairly robust by, at some point in time, simply disabling the GPS or have a GPS outage so that the GPS system doesn't work anymore. So you can actually disable the GPS or you have a GPS outage, but the visual odometry is still able to track the motion of the UAV accurately and estimate how the system is moving through the environment. So at some point in time when the GPS comes back and recovers, or you activate it again, you can actually show that the estimates that both systems actually generate are very close to each other, and without any jumps or serious inconsistencies, you can actually provide this joint estimation of the position through the GPS IMU combination and the camera data. So it's a great way of actually combining techniques from geodetic surveying and GNSS systems to and photogrammetry in order to get the best out of two worlds and enable robots to do things they would be otherwise not able to do. And then there is a second example that we have over here, where we have the drone actually flying around, estimating its pose with this tracking system, and then being able to take the sensor data from the high-resolution camera to perform a 3D reconstruction based on these images. So basically, let's call it a glorified triangulation from these multiple images, something that we call bundle adjustment, and that uses these 3D points and can estimate the location of these 3D points, which you see the surface of the building, and then perform, in the end, a 3D reconstruction of that building just based on those points. Or at least can measure substantial parts of that image, and then we can actually compare how accurate are those point clouds that I'm generating from my camera data by overlaying them with the reference point cloud here generated with a high-resolution laser scanner, for example. And you can actually see that the similarity of the points that are generated from the camera and of this high-resolution laser scanner, they are actually very close to each other, and you get an accuracy here of the order of median error of in the order of 1 centimeter out of this, just by using a UAV flying around and observing the scene. Again, you can compare this to a terrestrial laser scan, which typically has a higher accuracy but also takes much longer, and you can see that those points are lying on that surface, and again, typically a median error of something around 1 to 2 centimeters is something that you can achieve here. I said orthophotos already, so if you have aerial imagery, then we are also looking into problems of correcting those images so that we can directly perform images in those aerial photos, so that we can directly measure distances in here. For that, we need some 3D information that we can estimate, or digital surface models, and through the combination of digital surface models and camera data, we can compute those so-called orthophotos. There's also similar techniques for 3D mapping, allows us to perform city mapping. So we have a mobile mapping vehicle equipped with cameras and can navigate through the environment. So this is a mapping vehicle equipped with 8 cameras developed by Geoautomation in Belgium. And you basically have these individual images. From these images, feature points are extracted. These are those points that you see here on the side, which are from the sideward-looking cameras. And by making the data association between those images, you can see here how the cameras are arranged. You can actually navigate through the environment and build 3D reconstructions of the city. And The 3D reconstructions are now built just for those distinct points, but of course you could also overlay this then with the image information that you have in order to build 3D models of the scene. And you can actually drive around for quite a while and then actually build large maps at city scale or even country scale by using this information. And also there are systems now using all the data from Google Street View for doing basically a worldwide bundle adjustment and computing 3D points based on the information collected from camera data. And then of course you can use this for mapping purposes. So this was the work done here in Leuven in Belgium for building maps, performing city maps, so that you can actually then use those city maps to either generate classical maps as we know them, but you can also actually go back and actually generate virtual fly-throughs through those 3D point clouds that you have been created. And you can also use this to build 3D city models. So this is a very old work done in the Bay Area on the 3D reconstructions. Nowadays you find more accurate 3D models of the environment. So there's an example from Berlin, virtual 3D city models which are generated using techniques based on image data, where you do 3D reconstructions of the scene or combining image data with other sensors and other sensing data. And this is also a common technique, common application of photogrammetric techniques together with other sensor data interpretation techniques. There are a few more interesting examples I would like to point out. So this is one digital heritage preservation, where these are images from underground catacombs in Rome. So under Rome, there are a lot of catacombs, in Italy in general. And the question is, can you explore those underground environments and actually build maps? And they're actually very huge, and it's a certain health hazard to address them, but they have high cultural heritage. And so what you can do is you can actually build robots that actually explore those scenes. So that's the project that we have been executing between 2013 and 2016 or 17, also here from Bonn, with this platform equipped with multiple cameras in order to perceive the environment and then perform 3D reconstruction based on those images, and then exploring those underground environments. And this is an example here of the Catacombe di Priscilla in Rome, where you see the 3D reconstruction of the entry into that catacomb explored or mapped with a mobile robot. So those blue areas are areas that have been occluded based on the low viewpoint of the platform. But what you can see is you get actually fairly accurate 3D reconstructions. And these are 3D reconstructions just generated based on the camera images, and was done using the structure for motion and bundle adjustment system developed by Luc van Gool's group at KU Leuven. And they did an outstanding job in doing these 3D reconstruction. Again, this doesn't work online. This is something which requires a substantial amount of compute, but you can actually build fairly large-scale scenes and large-scale maps with this. So that you then can actually overlay this. So this is a whole catacomb map at Priscilla in Rome. You can see here part of the environment that we had been exploring with our robotics system at that point. In general, robots are a great platform to use the techniques developed in photogrammetry and computer vision in order to perform tasks. This can be simple navigation tasks, this can be your Hoover or your lawnmower, or this can also be an autonomous car. And what all those systems need to do, they need to observe the environment, observe their surroundings, and interpret what's going on, and then make decision on what they see. So they need to know where they can navigate, they need to know what is in front of them. And for that, semantic plays an important role. So semantic can be in a driving scene that you say, okay, these objects here are actually cars. This is a bus. This is my drivable surface. These are road markings. These are people. This is vegetation. This is building. This are street signs. So you need to have this information in order to estimate what you want to do. Or you want to detect where are people in the scene. So basically everything which is marked here in green are persons identified by a camera system and performing a semantic interpretation, so that robots can use this information, for example, to interact with people or to filter people out of their state estimation processes if they only want to build maps of static scenes. So there's a large variety of possibilities that you can have and how you can exploit those techniques. There's also other questions in this context are visual localization. This goes then a little bit more to the autonomous driving domain. So the question, for example, is this the same place? So you see here two images and you should ask yourself, is this the same place, yes or no? And it turns out it's actually a tricky question. One image was taken in summer, the other one was taken in winter, but actually it was the same place. It looks a little bit different due to the vegetation, some snow around, completely different image purposes. And it turns out it's actually quite hard if you take images at different points in times and different locations under different weather conditions at different seasons to actually make that data association. And this is an example of image pairs taken from the same place, either during different weather conditions, day and night, summer and winter and spring. And so the question is, how can you actually make this data association? How can you match those images? And these are also techniques you can look into and then use this to build localization systems that you have one part of the scene, which is a reference map, so reference images, it's a georeference taken at some point in time. And this is a current sensor stream that you have in here where you want to estimate a platform just based on visual information. And you can actually navigate through the scene and want to match the summer-winter against the winter images in order to perform localization. And this is one form of visual localization which is agnostic to seasonal changes, so does a cross-season localization in order to estimate a vehicle. And these are relevant tasks that, for example, pop up in autonomous driving. Again, autonomous driving became a popular discipline, let's say 15 years ago. There was a larger breakthrough there of making autonomous cars more and more popular. So this is an example of the Google car around 2009, I would say, when Google released the first car, which does a lot of tasks by using this laser scanner, which sits here on top and observes the scene. Also equipped with cameras and radars and some other sensors. And what the car actually sees is this type of point cloud. So this is a rings of range measurements. And what now needs to be done, you need to interpret the sensor information or to estimate where to go. Is it safe to navigate somewhere? Are there other traffic participants around? What's going to happen in the future? These are all relevant questions that you want to answer based on your sensor perceptions. You can start out with cameras doing a semantic interpretation or semantic segmentation of the scene. So what you see here is the input camera image and an algorithm that we have developed here in my team on performing semantic segmentation, meaning you want to assign to every single label in that input image a color value which tells you what type of object it is. Is it a human? Is it another car? Is it a tree? Is it a traffic sign? And these interpretations, doing them in real time at whatever 50, 70 frames per second is a challenging task if you want to do this fast. And these are techniques using machine learning algorithms in order to perform this, what is called semantic segmentation of the scene, which is super relevant for autonomous driving. And by now we can even do this on LiDAR data. So again, this is a similar setup that we've seen the other car before, using the same 64 beam Velodyne laser scanner, scanning the environment. And here the colors of those points actually refer to semantic classes, so that you can track different objects and see what's going on in there. And through the semantic information can, for example, filter out certain parts of the scene. And this is kind of the next step. So this is LiDAR-based semantic segmentation. And if you now want to go a step further, what you actually want to estimate together is kind of, you want to extract pose information in 3D geometry, something we kind of know how we do that. We want to extract semantic information. These are the color labels here saying this is road, this is a car. You want to get instance information. That means you want to say, okay, this is car number 1, this is car number 2, this is car number 3. So you just don't want to say this point is a car and this is also a car. You actually want to have the individual cars being identified, which then is important if you want to track those cars. How do they move through the environment? In order to then make predictions about what's going to happen in the future. Because you want to make prediction about what's happening in the future in order to estimate what to do. And these are tasks which are highly relevant in autonomous driving, where you need to combine information from sensors such as GNSS, IMU, camera data, LiDAR data, odometry information, to estimate 3D geometry. Use your cameras, you use your LiDARs to estimate semantics. You use this information also to extract instances, doing tracking, doing predictions, and then feeding it into your planning system, into a decision-making process of what to do, where to navigate. And so these are key components that you need in order to realize autonomous driving applications, for example. And this brings me to the next video, which is actually an advertisement video by Waymo, which is one of the companies who works on autonomous cars, introducing what they are seeing, how their system works, and which information they are using. And what you see if you look to that, a lot of technology that you see in happening there is actually something that is used in photogrammetry. This can be estimating where we are, using 3D point cloud data, estimating where they are humans. These are all tasks which play an important role, and I just show this video as a motivation for you why this information can actually be useful.
Waymo uses LiDAR, which sends out millions of laser beams per second to build up a detailed picture of the world all 360 degrees around it. It also uses radar to detect how far away objects are and their speed. And high-resolution cameras detect visual information, like whether a traffic signal is red or green. It then combines all that data to understand the world around it. For example, in this fraction of a second, it knows exactly where it is on the road. It can also identify everything around it in full 360 degrees, and then predict what those things might do next. And it doesn't just do that for the objects you and I can see. It can do that for things up to 3 football fields away. What makes everything you can see right now possible is experience. Waymo has already self-driven millions of miles on complicated city streets, and it's constantly learning from every single mile it drives. With all that knowledge, it can plan a safe path ahead. In this instance, giving that cyclist enough room to cycle past us, and also looking out for that pedestrian on the sidewalk. And when it comes to making decisions, this is a good example of how Waymo doesn't just take into account your safety. It also makes sure that both you and the people around you feel secure and at ease. So now that you know how Waymo works, it's time to take your first ride in one of our cars. Take a look around. You're now riding in a fully self-driving car. Some things might immediately stand out. The fact that there's no one in the driver's seat, no one turning the wheel, and the screens, which show you what the car is seeing and the route it's taking. But you might also notice that the ride feels a lot like being driven in a regular car. And that's the way it should feel. All this technology, which allows Waymo to see, identify, predict, and plan, should make an extraordinary ride feel completely ordinary and create a very normal journey that simply gets you from A to B, safe and sound. And while it does all that, all you have to do is sit back, relax, and enjoy the ride.
And this actually brings me to the end of my introductory lecture. So again, this course will cover 2 parts, Photogrammetry I and Photogrammetry II. Photogrammetry I taught in the summer term, Photogrammetry II taught in the winter term. And what I want to do with this course is actually stimulate your interest in photogrammetry, computer vision, robotics, and learning-related aspects so that you learn how to interpret sensor data, mainly cameras for now. Later on, we'll extend it also to LiDARs, for example, in further courses, that you understand the foundations of photogrammetry, how can we do 3D reconstructions, how can we interpret a scene, and how can we use these information in modeling, in state estimation techniques to estimate what the geometry of the world, where are we, and kind of confuse this information as building blocks for realizing cool systems. This could be building blocks for autonomous cars, for robots navigating around, for environment monitoring purposes. There's a large variety of different applications, and I want to teach you the basic concept that you need to understand in order to realize those applications later on. Of course, if you want to build the state-of-the-art top-notch system, you need to dive deeper, but this course should be a pretty good starting point for your future investigations. People often ask me in terms of which literature do I recommend. So there are different things that I have been using here or will be using in this course. Although I think the course is self-sustained enough that you actually don't need to buy additional books. So one, which is great, is Wolfgang Förstner and Bernd Wrobel's Photogrammetry Computer Vision book. It's precisely written. It's not necessarily an easy read, but if you really want to dive deep and get the proper understanding what's going on, especially for the geometric concepts, that's my #1 book to look into. This becomes especially relevant for the end of the Photogrammetry I course and Photogrammetry II course. It doesn't cover things such as machine learning aspects for image interpretation tasks, for example. There's a script by Wolfgang Fürstner's lecture, which he was teaching here until 8 or 9 years ago, which still has a substantial overlap with my lecture, but maybe only up to 50–60% by now. I kept his notation, so that's something you may want to look into if you want to have additional reading material. There's a book, Computer Vision, Algorithms and Applications, dating from 2010, which also some of the examples, especially initially in the course, in the first part, are taken from that course. When it comes to machine learning, I really like the Alpayadin Introduction to Machine Learning book because it's really easily written and very easy to understand. Does everything first in 1D and then generalizes to ND cases. So I found that a really, really good read. And then there is, of course, the classical multiple view geometry by Hartley and Sisserman, which is kind of one of the Bibles of, let's say, geometric reconstruction from images. And so it's basically similar to the first book over here. Some people prefer the photogrammetric computer vision book more. Some prefer the multiple view geometry more. I kept my notation with the photogrammetric computer vision book, but both of them are great books and a great read. So with this, thank you very much for your attention, and I hope you will stick with us in this course, learning all these interesting concepts. Thank you very much for your attention.